Hi everyone, and welcome to the Antibiotic Sensitivity Testing Lab, also known as the Kirby Bauer technique. Start off with just a quick scientist spotlight. This is Jane Hinton. There's a lot of white male scientists featured in our textbook and in microbiology history, so I've been trying to do the work to find some more, underrepresented microbiologists in history, and this one was interesting. So the media that we use in this lab um, is called Mueller-Hinton agar, and it's named after John Howard Mueller, who was a white male, and Jane Hinton, who was a black female scientist. And she is really credited with designing this recipe for this media that was originally designed to grow Neisseria species, so Neisseria gonorrhea and Neisseria meningitidis, but was later adapted for this antibiotic sensitivity testing. So she was a pretty outstanding woman. She worked at Harvard with John Howard Mueller, and then as a lab tech, and then she left to earn her veterinary degree, which she was one of the first two black women to ever graduate with a veterinary medicine degree. So, cool stuff. All right, antibiotics and antibiotic sensitivity testing. So, we know that antibiotics are compounds that are made by microbes that antagonize other microbes or kill other surrounding microbes, first identified by Alexander Fleming, and this is not his plate, but an example of what his plate might have looked like. Here is a penicillium mold, and here is some bacteria that was swabbed on the plate, and around it you can see this zone where there is no growth, as if the bacteria are kind of like too scared to get too close to that penicillium mold. In fact, the penicillium mold is secreting a chemical that is antimicrobial, that kills bacteria, and so they can't grow. We call that area the zone of inhibition. And so now we're in this, antibiotic crisis where microbes have evolved resistance to the antibiotics that we throw at them. And so before treating someone with antibiotics, it's important to test the pathogen that's causing their illness and determine which antibiotics it is sensitive or resistant to, because we can no longer just assume, based on the species, that it's going to be sensitive to a specific antibiotic. And so this is a Kirby Bauer testing technique. When it's ordered in a clinical setting, it's often called a culture and sensitivity test. So they swab your bacteria, the pathogen that's causing your disease, all over the surface of the plate, and then they dot the plate with these antibiotic-soaked discs and look for these zones of inhibition. So when we do this test, technically it's called the Kirby Bauer disc diffusion test, though again, in a clinical setting, you usually call it culture and sensitivity test. And you measure these zones of inhibition. So you're measuring the diameter of that circle where there's no growth around the disc. Okay, we measure it in millimeters. The larger the zone of inhibition, the more effective the antibiotic is. Or in other words, the more sensitive the organism is to that antibiotic. So a large zone of inhibition means that the bacteria is sensitive to that antibiotic. If it has a small or nearly non-existent zone of inhibition, it means that the bacteria is resistant to that antibiotic. And if it has a medium size, then it's an intermediate. It has intermediate effectiveness against that bacteria. And so in a way, you can kind of just eyeball and determine whether the antibiotic is appropriate or not. If it has a very large or very small zone of inhibition, if they're a lot of sort of medium-sized, then you need to do your measurements for sure. So quick concept check with these pre-lab questions. Why might microbes produce chemicals that are inhibitory to other microbes? Why is that? Why would they do that? And then in this picture on the right, which antibiotic discs do you think the bacteria is sensitive to? All right, and also note that it's the bacteria that is sensitive to the antibiotic. Right? The antibiotic is not sensitive to the bacteria. The bacteria is sensitive to the antibiotic, and that wording is important. And then number 3, which antibiotic discs do you think the bacteria is resistant to? So just, based on eyeball, write down your answers for that. So antibiotics, of course, have different mechanisms of action. So they have different targets in the cell. Some common targets, one is some target cell wall synthesis. So these are all ways in which they remain selectively toxic to bacteria and not eukaryotes like ourselves. So eukaryotes do not have peptidoglycan cell walls. So targeting the cell wall is a common target. They can also, antimicrobials can also target transcription and translation. Now, transcription and translation are very similar in prokaryotes and eukaryotes, but the RNA polymerase of prokaryotes is different than the RNA polymerase of eukaryotes, and the ribosomes in prokaryotes are different than eukaryotes. So you can still find chemicals that are selectively toxic to the prokaryotic versions of those enzymes and don't affect the eukaryotic versions. They can also do damage to plasma membranes, and they can damage biochemical pathways that are unique to prokaryotes and are not found in eukaryotes. So pathways to synthesize vitamins, for example, that we get through our diet, but that microbes get through metabolism. And so this is just a very small selected table looking at the spectrum of activity of different antimicrobials. So some antimicrobials have a very narrow spectrum, meaning they only affect a small number of microbes. So penicillin is a classic narrow spectrum. It has a much more better effect. It's much more effective against gram-positive bacteria than gram-negative bacteria because penicillin affects the cell wall. And gram-positive bacteria have a thick cell wall, a thick peptidoglycan layer that they're very dependent on, versus gram-negatives, which just have a very thin peptidoglycan layer, and then they have their 2 cell membranes. They have 2 membrane layers, which is why polymyxin is really much better at affecting gram-negative bacteria because polymyxin injures the plasma membrane, and gram-negatives have 2 plasma membranes, and so they're much more sensitive to the polymyxin. Whereas some drugs on here like erythromycin, tetracycline seem to have a broader spectrum. They can affect many different types of prokaryotes, gram-negative, gram-positive, and chlamydias and rickettsias. So they have a wide range of microbes that they can target. And they are ones that target the translation, the ribosome. So the ribosomes of all these different types of bacteria are pretty conserved, even though their structures, their outer structures are very different. So the 2 bacteria that we used in this lab, we used E. coli, which is our gram-negative, and we used Staph saprophyticus, which is our gram-positive. We've got a gram-negative rod and a gram-positive coccus. So comparing 2 different types of microbes and their different susceptibilities or sensitivities to antibiotics. Just some fun facts about these. E. coli and Staph saprophyticus are both normally they're normal microbes, but they can cause infections. Particularly, they are guilty of causing urinary tract infections, UTIs, in especially in patients that are catheterized. So Staph saprophyticus can come from the skin, and so if somebody didn't sterilely handle the catheter, or even just the catheter becomes contaminated on introduction into the urethra from the patient's skin, then it can become colonized with Staph saprophyticus and introduce that to the urinary tract. E. coli is normal flora in the gut, and so sometimes it accidentally gets from the anus to the urethra and causes urinary tract infections that way. So these are both clinically relevant. However, the strains that we are using, very unlikely to cause infection when working with them. They are BSL, biosafety level 1 organisms. So the experimental overview, what y'all already did was you labeled a Mueller-Hinton agar plate, and you used a cotton swab to completely inoculate a lawn of bacteria onto the plate. And then you placed 4 different antibiotic discs around the plate, and we incubated them, and the lawn grew, but there were on some of them, there was a zone of inhibition around some of those antibiotic discs. And so today's task would be to measure that zone of inhibition and determine whether the bacteria was resistant, sensitive, or somewhere in the middle, intermediate, to that antibiotic. This is just the procedure you already did. This is the measuring procedure. All right. So when you measure the zone of inhibition, you're measuring the diameter, the widest distance across that circle zone of inhibition. If there is no zone of inhibition, you just measure the disc. So we really don't say that there's ever a 0 zone of inhibition. It's 6 millimeters is the smallest. If we were in person, I would have you all record the zone of inhibition for each of your plates, and then you would write the results on the board, and we would tally some statistics, we'd calculate averages. But since we're doing this remotely, I'm just having everyone do the same plates. So I guess I have these in the wrong order. This is the results. I can move this, and then it will be in the correct spot for yours. There we go. Okay, so this is the results slide. So it's just one plate of the Staph saprophyticus and one plate of the E. coli. And I have a ruler here for you to use. And so you're going to use the ruler to measure the zones of inhibition. And you can do that by, I'm clicking the zoom button here at the bottom of the screen. You don't want to blow up the plate, so don't resize the plates or the ruler. They are the correct proportional sizes to each other. So what you can do though is you can zoom in, and now we can see the measurements on the ruler really well, and we can see the zones of inhibition really well. So for example, for the S, which is the streptomycin, all right, I'm going to bring my ruler here, and I'm going to measure from this end to this end of the circle. Now this is in centimeters, but we want our units to be in millimeters. So remember, there's 10 millimeters for every centimeter. So this is about 2.4 centimeters across, which would be 24 millimeters. So we would record this zone of inhibition as being 24 millimeters. And you will record that, maybe initially record it on a sheet of paper, and then you can transfer it to this table here. So make sure that you are recording your measurements under the correct plate. So Staph saprophyticus is on the left. And so the zone of inhibition, that is what you are measuring, and you're going to put here. and then E. coli's zone of inhibitions you will put here. Then you will refer to the table on the previous slide to check whether that zone of inhibition qualifies as resistant, intermediate, or susceptible. So we just said that streptomycin had a zone of inhibition of 24 millimeters. So streptomycin here on the table, 24 millimeters is greater than 21 millimeters. So it is susceptible. If it's greater than this number here, it is susceptible. If it's equal to or less than the number here, then it is resistant. And if it's somewhere in between the two numbers, then we would say that it is intermediate. So back here on this table, where we had recorded 24, all right, for the streptomycin zone of inhibition on the staph saprophyticus plate, we can say that that is comfortably sensitive, RSI, resistant, sensitive, or intermediate. So you would do that for all of these. All right, then I do want you to do a little bit of sketching. So basically what I'm asking you to do here, oh, just kidding. Yeah, I'll delete this slide. Okay, you don't need to do sketching since the plates are right here. It's clear what they look like. And here's your results table. So then I do want you to write some conclusions. So based on your results table, which antibiotics were the staph saprophyticus resistant to? Which antibiotics was staph saprophyticus sensitive to? Same thing for E. coli. And then also, based on the mechanism of drug action, explain why E. coli is less susceptible to penicillin than staph saprophyticus. And based on our results, so not based on the table above on the slide 6, okay, not based on this table here, but based on the results that we got, which antibiotics do you think are broad spectrum? Okay, and why? Explain why. So it might not be consistent with what we had determined up here. And I will confess that my antibiotic discs are kind of old and a little expired, and so some of them might not be working as well. So that might give us different results than what we would have expected based on this. So just consider that. All right, if you have any questions, I will be available during Zoom office hours review/review session at 8 p.m. tonight. Feel free to drop in or shoot me an email. And that's all.